So the take-home portion is pretty much just a homework assignment. You, yeah, I mean, that's literally pretty much it. It's literally just the homework format, but instead of being over one specific topic, it'll be over multiple topics kind of thing. Yeah, pretty much, yeah. Yes. So there'll be some hand analysis and there will be some LT Spice stuff too. Yeah. So like I'm gonna have you, I'm gonna upload your design project, your first design project today. I say today, within the next day or two, because this is the last topic on op amps and your first design project is all about op amps. You'll have a selection of different circuits, that you could design. I think I'm asking you for maybe 2 out of 4 or 5 or something like that. On your take-home exam, there will be one problem that is associated with design that everybody has to do because it's on the test kind of thing. So it should be like one op amp analysis problem, I think, where I'm going to have you use the practical op amp model. I'm not going to have you use the practical op amp model for on the take there. It's going to be the in-class portion of the test so much because it's a pain in the ass to do that analysis, or at least for a negative feedback circuit anyway. So it should be one problem, negative feedback problem with the practical op amp model, a design problem, and then I'm trying to remember what else I usually do. Something else, and then the design problem will definitely have an LT Spice component of you simulating stuff to make sure that you meet the design criteria. Did I not do that? If I didn't do that, please send me an email to remind me to do it, and I will do it later today, hopefully. But yeah, and we're all aware that the test is Monday, correct? Okay. All right. Okie dokie. So today we're going to talk about cascaded op amp circuits, and this is going to be short because we already know 90% of the material. Okay. So what I'm going to be dealing with today is specifically cascading negative feedback op amp circuits together, but there's nothing preventing us from cascading a combination of positive feedback, negative feedback, or even open loop circuits together. Okay. So in the most basic form, a cascaded op amp circuit is literally nothing more than chaining the output of one op amp circuit to the input of another op amp circuit, and so on and so forth in order to get to do more things, right? So I'm going to draw a simple negative feedback cascaded op amp circuit here. So let's say that we have something like this. So here's our first op amp stage. And I'm going to call this op amp A1. We have some supply voltage, VCC plus and VCC minus. And let's make the first stage look something like this. So let's call this a 10 kilo ohm resistor. Over here, let's make this a 4 kilo ohm resistor. This will be our negative. This will be our positive. Let's make this ground for the sake of argument. Let's apply a simple DC input voltage here just because we're seeing what happens of 3 volts. Okay. And then over here, let's have a 2 kilo ohm resistor. This will be op amp A2. It also has the requisite supply voltage is connected. Let's make this also a 10 kilo ohm resistor. This will be the output of the cascaded op-amp circuit, and I'm going to ground this guy. Okay. So this is a cascaded op-amp circuit again, just because the output of our first stage, which would be this node right here, is chained into the input of our second stage over here. So all we're doing is just stringing together circuits, and we're going to get the combined effects of all of the circuits. Okay. So we are going to analyze this circuit. I'm going to call it the hard way first, but it's not particularly difficult. And then we're going to go back around and talk about looking at it from a different perspective here. Okay. So the hard way is going to be effectively applying the rules that we've used previously to analyze negative feedback op-amp circuits. So I can observe from the jump here that this current is 0 amps. This current is 0 amps. I forgot to give this resistor a value, so let's call it 1 kilo ohms. This current is 0 amps. This current is 0 amps. We can see by inspection, I think I was using green before, that the voltage present at the non-inverting input terminal of op-amp 1 is going to be 3 volts, which means the voltage at the inverting input terminal of op-amp 1 is also going to be 3 volts. The voltage at the non-inverting input terminal of op-amp 2 is 0 volts. And so the voltage present at the inverting input terminal of op-amp 2 must also be 0 volts. And now we're going to wind up applying Kirchhoff's current law here, as well as here, to get our relationship for our output voltage. So in order for this to work, I am going to just call the voltage here with respect to the ground Vx, just because I need a label for this voltage to use in my KCL equations. So applying KCL at the inverting input of op-amp 1, we get the relationship of 3 volts divided by 4 kilo ohms plus 3 volts minus Vx over 10 kilo ohms is equal to 0. And if we applied KCL at the inverting input of op-amp number 2, we would get 0 minus Vx, so negative Vx over 2 kilo ohms plus Vx minus V out over 10 kilo ohms is equal to 0. And then we could solve this system of equations for Vx and V out. Isaiah. You're correct. It should be 0 minus V out. Thank you. So just negative V out over 10 kilo ohms. Thank you for that, Isaiah. Yep. So we have 2 equation, 2 unknown system, except that we really don't, because there's only one unknown quantity here, and that unknown quantity here feeds into this thing. So realistically, if we solve this one equation, one unknown system, then we have a one equation, one unknown system here. So let's solve for this voltage Vx pretty quickly. So Vx is going to be let's see, so I'm going to have 3 volts over 4 kilo ohms. Plus 3 volts over 10 kilo ohms. This whole thing multiplied by 10 kilo ohms, right? Doing my algebra here. So 3/4 plus 3/10 times 10, 21 over 2. .5 volts if my algebra is correct. Let me just see something here. Yep, 10.5 volts. Substituting that 10.5 volts into here, we would have V out is equal to negative 10.5 volts times 10 kilo ohms over 2 kilo ohms. Is negative 52.5 volts. So we'd have to have a pretty damn beefy op amp to be able to give us an output voltage that high, or at least accept very, very large supply voltages, but that's not really what we're looking at here. Okay. So this process is the hard way, and it is not particularly difficult, but we could make this wildly easier by making a couple of simple observations. If I ignore literally everything to the right of this dashed red line, what does this op amp stage look like? A what? What's normal? And so it's definitely negative feedback. Both of the stages are negative feedback, but this is a particular type of amplifier that we talked about in class the other day. So which particular type of amplifier is it? A non-inverting op amp. Okay. The input voltage is applied at the non-inverting input terminal. We have negative feedback, all that kind of stuff. It's a simple non-inverting op amp. How do we find the output voltage of a non-inverting op amp? 1 plus, so the input voltage times 1 plus the feedback resistor over this resistor. What's 3 volts times 1 plus 10 over 4? 10.5 volts, which is exactly the voltage that we got at the output terminal of that stage, right? Now, let's say that everything to the left of this dashed red line looks like a voltage source. What type of amplifier is over here on the right-hand side? Yep. So an inverting amplifier, how do we find the output voltage of an inverting amplifier? Times the input voltage, okay? So the input voltage Vx, which was the output of our first stage, is fed into the input of this guy. We multiply that Vx by negative 10 over 2, which is exactly what we wound up doing down here. So instead of going through all of this analysis, if we can recognize what our stages are and we know what the input-output relationship for each stage is, we can literally just chain all that together. So we could really think of this as we have some amplifier stage A1. Our input voltage is 3 volts, and we know that the voltage gain of stage 1 was 1 plus 10 over 4. Chained into some second amplifier stage, A2, where the voltage gain of stage 2 was negative 10 over 2. And here's our output. So we are literally going to have V out is equal to V in, which was 3 volts, times the voltage gain of stage 1 times the voltage gain of stage 2, where these guys tied together is just the voltage gain of our system. So we don't have to do any analysis at all to analyze a cascaded combination of negative feedback op-amp circuits, as long as we understand what each stage is, right? So if we were going to cascade together negative feedback and non-negative feedback circuits, we really just need to understand what each stage is doing to understand how things are going to work, right? So for instance, if we fed a differencing amplifier into a comparator, that would be effectively us saying we want to make sure that the difference between two input signals doesn't exceed some arbitrary reference voltage or something like that. That's something that we might need to do in a control system or something, right? We could, excuse me, take the difference of two signals and then integrate that output or something by cascading a differencing amplifier into an integrator, or cascading a differencing amplifier into a differentiator, or we might want to take the integral of a combination of input signals. But it's all just simply putting the stages in the order that we want the mathematical operations to occur, right? So for this is very, very boring because it's just scaling twice, and we could have accomplished this with a single amplifier, but I was just trying to show you how it worked. Realistically, we can chain any number of stages that do different things together to perform more complex mathematical operations and all of that kind of good stuff. And that's where cascaded amplifiers get interesting, which is why I have you design some of those things. I'm done. So effectively, unless it's something that you don't know how it behaves, just break it down into stages and then use those relationships. If it's something that you don't understand how it behaves, then you have to analyze it the long way. That's cascaded amplifiers in a nutshell, right? So on your homework assignment, I give you something probably similar to this, and then I also do something like this. Let me do it in blue here. So I feed back the output of the second stage to the input of the first stage. Is this something that we've seen before? Absolutely not. So you would have to analyze this circuit using the long method. But if it's nothing tying the output of the second stage to the input of the first stage or something weird like that, just break it down into more digestible parts and call it a day. Doesn't have to be hard unless you want to make it hard. So on your exam on Monday, I'm going to give you cascaded op-amp circuits, and I'm literally going to draw big boxes around each stage. And I'm going to ask you, what type of amplifier is stage 1? What type of amplifier is stage 2? What type of amplifier is stage 3? And then I'm going to say, for your input signal of blah, what's the output of this stage? And then use that to feed into the next stage and so forth. So my expectation on those problems is that you literally do no circuit analysis whatsoever. You simply use the equation sheet and go, this stage looks like that picture, which means I use this relationship. And then do that stage by stage by stage. So stop freaking out about this test. It's not that hard. I think it's like 8 or something like that. So it's not 25 or anything ridiculous like circuits 1 because you only have an hour and 15 minutes to do it. Realistically, and I'm gonna sound like such a dick, but I'm gonna say it anyway. I would be concerned if it took you more than 45 minutes. Like if it takes you more than 45 minutes, you probably weren't paying enough attention or you didn't do your homework. I say that knowing that I'm going to have a really good student who's going to take the full hour and 15 minutes. I'm going to feel like a total jackass, but that's my immediate thought is realistically, this test shouldn't take you longer than 30 to 45 minutes tops if you know what you're doing. It always shoots me in the foot when I say something like that. So that's my honest opinion. Yes.
So are they going to be named like weighted inverting summer or just negative, positive amplifying, negative feedback?
So let's look back at the equation sheet that you guys are going to have access to, and also I need to upload for you guys to look at. What's this thing in chat say? Equation sheet. Thank you, Michael. I'm going to show it up here on Zoom, and also you're going to have it for the test. Let's see. Oh, right here in the files I opened recently. Open it. So going back to the negative feedback op-amp circuits, I literally tell you the name I'm expecting you to write down as well, right? A non-inverting amplifier. Just to be really clear here, I might throw you a little bit of a curveball and maybe flip this part over or something like that. With the positive, the non-inverting terminal, the non-inverting input terminal is on top, and the inverting input terminal is on bottom. But we can still see that it's a non-inverting amplifier because the input signal is applied on the non-inverting side. And then the feedback is negative feedback like here, and ground is there, right? Here's an inverting amplifier. Again, it's the exact same circuit, except that VN and ground are switched. This guy right here, an inverting summing amplifier, differencing amplifier, differentiating amplifier, integrating amplifier. Those are the 6 that you need to be able to identify on site. And again, you're going to have this literally in front of you. So it shouldn't be that hard to do. It blows my mind how many students can't do it, but it shouldn't be that hard to do. Lynn. Nope. Transient analysis, Thevenin equivalent circuits and all of that kind of stuff was just a review for crap you need to know in order to succeed in this class. So nothing like that on this exam. This exam is strictly op-amp related material. Yes, Toby. I mean, I just depends. So those resistors, and we can identify them here really quickly. You're not going to get this updated thing, but so putting a load resistor here is definitely fair game. Putting some resistance here, definitely fair game. That same resistance could show up here. Could have a load resistance here. This guy, again, we could put a resistor there, load resistor here. For this guy, the only thing that I could arguably try to trip you up with would be a load resistor because all of the other resistors are important. For the differentiating and the integrating amplifiers, again, could put a load resistor, could put a resistor in series. Does not impact the analysis in any way, shape, or form. And you can see that it doesn't impact the analysis in any way, shape, or form simply by applying the ideal op-amp rules. So definitely, I might throw them on there to trip you up, but I've told you explicitly that they don't do anything, so hopefully it's not that confusing. Yes, Walter. I have to go back and look, but probably somewhere in the ballpark of the 80s. So like I said, if you've done the homework and the homework makes sense to you, this should be easy. Michael, I just said that putting resistors in those particular places will not change the equations at all. And if you watch the lecture video on common negative feedback op-amp circuits or whatever the hell I named it, last time's meeting, I talked about why it doesn't impact anything and all that kind of good stuff there. Sorry, did I answer your question, Walter? I got distracted. Okay. Yep.
Are we gonna work today?
You are getting a homework today. Would it be due Monday? Yeah, it would be due Monday. Yeah. So I had one. There was one for, so last Friday's class meeting, I think I said something about I wasn't gonna put a homework up and then I wound up changing my mind. And so I made that due on Thursday because I didn't put it up on Friday to give you guys plenty of time to work on it. Because since it was assigned, if I had actually assigned it on Friday, it would have been due on Wednesday. But I pushed it back a day because I didn't get it up in a timely fashion. And so to avoid you guys having homeworks due literally back to back, the homework set that was associated with what we covered on Monday, I moved that due date to Saturday so that you have a little bit of time, because I know how much you guys and myself procrastinate, so that you wouldn't have to do two homeworks back to back, so like straight back to back like that. Yeah, so that's why it's the odd dates there, me attempting to be arguably nice. Yep.
So on homework 6, the one that was from Monday's class,
Mhm.
we had to derive the equation.
Mhm.
Will there be something like that on the test or no? You've already done it.
If I do anything like that, it would be on the take-home portion of the test, not the in-class portion of the test. It doesn't take a particularly long amount of time, but it's long enough and makes you think enough to where I want you to have plenty of time to do it.
And the probability.
Yeah. I mean, it could have, I don't know if it was a differentiator, but I could give you an integrator or something like that, but yeah. Something like that problem that's the other problem on, the take-home test that I couldn't remember. I don't make you derive anything per se, but I give you either a differentiator or an integrator, and then I give you a time varying function and make you tell me what the output's gonna be. Kind of thing. So you can go through the analysis, or you can look at it and say, hey, this is an integrator, so I know it's gonna behave this way. Or hey, it's a differentiator, the opposite of whatever the hell I just said, so I know it's gonna behave this way. I think I broke it down into little bitty steps to guide you through effectively the process, almost like you were deriving what the output should be based on the input voltage, if I remember correctly. But yeah. I think it's like 8 questions on the in-class and it's 3 on the take-home. I may be misremembering. It's treated just like a homework. So exact same format as a homework assignment. If I remember correctly on the instructions, I literally say use standard homework formatting procedures or something like that.
Divided by 81.
75, 25 or something. Actually, it's probably more like 75 and then 30. So I usually have a little bit of bonus built into either the in-class portion or the take-home portion, but not both. So that it all comes out to be out of 105. So the test is graded out of 100. So there's effectively 5 bonus points to be made if you do well, or 5 bonus points to fix things if you screw stuff up, whatever way you choose to look at it. And very often, so I'll say this specifically on Moodle because I don't know what the hell I'm doing on Moodle. Usually the in-class portion is graded, or the take-home portion wound up being out of 100 points because of the way that assignments like default or everything. But realistically, what you should do is when you get your in-class grade and you get your take-home grade, add them together, and that's your total score, for example. So I don't care what Canvas says or whatever the hell we're using, add those 2 results together. That's your score. And then the weight on Canvas or whatever is probably going to be wrong, but it's going to be wrong regardless because of that policy where whichever test you do, the worst on only counts for half or something like that anyway. So your grades on Canvas for an individual assignment should be correct. But your final grade in the course on Canvas, just like Moodle, is always going to be wildly wrong. You're engineers, you have a rubric in front of you, you know how things are weighted, use Excel, figure shit out. Anything else? All right, you guys have a great rest of your day.